Okay, welcome everyone to the 136th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Julia Schneider from the University of Burgundy, and she'll be talking to us about atomic decompositions for derived categories for G surfaces.
Okay. So thank you a lot. So thanks a lot for this invitation. So the project that I will talk about today is between derived categories and birational geometry. And so I'm definitely coming from the side of birational geometry and not from derived categories. So, well, it's going to be interesting to speak here since this is the seminar for triangulated categories. So, okay, so really I want to emphasize, so my side is coming from birational geometry and not derived categories. So, yeah. So, so in general, if you have any questions, please ask. Okay. So I don't really know what I can assume as like things that people know or not. So, yeah, don't hesitate to ask. So I want to start with a conjecture by Kontsevich. And it says that so derived categories of smooth projective varieties admit canonical semi-orthogonal decomposition that is compatible with, let's say, geometric operations. So, okay, and so, okay, and I have to add here up to mutations. So this is maybe a bit a vague statement, maybe not, but this is like the setting that I will speak about today. So today, we're going to look at the decompositions of derived categories of surfaces. That respect, let me formulate it like this, that respect birational geometry. I will make it clearer in a bit. So let me quickly say something about birational geometry for surfaces. So this is like the easy case. So let's speak about the MMP for surfaces. So if we have Y, a smooth projective surface, let's say over a perfect field K, then there exists a birational morphism from Y to some X, so which is a composition of blow-ups of closed points. Such that we're one of two cases. So either first case is that X is a minimal model, which means that the canonical divisor is net. Or we are in the setting where the X admits a Mori fiber space structure. So we have X together with a morphism to some B, Mori fiber space. So what this means is So let's call it pi. So pi is a surjective morphism with connected fibers. It has relative pica rank 1. The dimension of B strictly smaller than the dimension of X. And the generic fiber is a Fano. And I should add somewhere B is smooth. Okay, so maybe it's not so important what these things are, but what I want to say here is that we have like these two different kinds of output, either minimal model or Mori fiber space. And so like a remark I want to make is that in the second case, when we end with a Mori fiber space, then the output of the MMP is not unique. So the X that we get is not unique. So the output is in general so what it means is that if we start with some Y, we can have a birational morphism to some X with a Mori fiber space structure, or also to some X prime, to some B prime, such that both of them are Mori fiber spaces. And then just to say, like the birational map that you get from X to X prime, this can be very complicated. So in this sense, you already get the complicated things. Okay, so this is all I wanted to say to MMP. So now let's take a derived categories. So what happens? So let me write it as maybe as a fact. So if F from Y to X is a MMP step. So what I mean by this now is one of the following. So that is either it is the blow up of a point, blow up of a point, or a Mori fiber space. Okay, so here when I will say MMP step, I really mean like either it is the blow up of a point or a Mori fiber space. And then we have that the derived push forward of OY is OX, and so this is called the derived contraction. And when this is satisfied, we have, and hence we have the formula that the derived category of Y admits a semi-orthogonal decomposition given by the kernel of the push forward and the pullback of dB of X. And so for this talk, so this formula is it's probably the most important formula. Okay, so let's do an example. So let's take, okay, let's start with maybe something a bit trivial. So we have a P2, so, okay, P2 is a Mori fiber space over spec K. And when we look at the semi-orthogonal decomposition, so we have EBP2 I write it here. O minus 2, O minus 1, and O. And just to say, like, okay, so the O, so this is like I don't know if this is the map F. So this is the pullback of well, of dB of spec k, if one really wants to write it in this way. Okay, so this is one example of this formula for, in the case for Mori fiber space. Now let's do a blow up of a point. So let's take a point in P2, let's blow it up. We get the Hilzable surface, the first Hilzable surface. And let's call E the exceptional device over the point. And so now F1, this admits, okay, so when we have the point, we have the pencil up lines through the point. So when we blow it up, we have a vibration to P1 that we get. And so this is again a Mori fiber space. So F1 over P1 is a Mori fiber space. So if we look at the definition again, so the generic fiber is P1, so this is Fano. And the other conditions are also satisfied. Okay, so this means now that when we look at, now let's look at the derived category of F1. And so first we can use the blow-up formula for the coming from P2. So what we get is OE minus 1, and then the pullback of the derived category of P2. So let me write O minus 2H, O minus H, O. But then on the other hand, we also get for like, okay, for from projective bundle formula, so coming from the map F1 to P1, we also get another SOD, namely we get, okay, so let me write it, let me write small h for the a fiber from P1. And so we get O minus E minus H, O minus E. Okay, and so this is what we get from the projective bundle formula. So we have these two different SODs of F1. And now in fact, so these are different, but in fact they are a mutation equivalent. So there is a mutation that sends one onto the other. And so in fact, the mutation that you can do is the following. So mutations, they act as the braid group on SODs. And like to draw it with the braid group, the mutation that one can do is the following. I just want to draw it because I like to draw things. So it is this one. Okay, so I'm not sure whether it's clear, but so what you can already see is that the O capital minus H, and so this one here, they are the same. So minus E minus small h. So this here is minus h. So we don't have to do anything with this. And so this corresponds then to this strand here which is not touched. Okay, but in general, like one has to do computations to see that this is the case. Okay. Now, I already have everything to give the main definition, I think, of today. So for this, first I need to introduce a category. So let V be a category such that so the objects, they are some class of varieties over K, and the morphisms are some derived contractions. And now I can give the definition of what the atomic theory is for this category V. Okay, so atomic theory for V assigns for all X in object of V a mutation equivalence class of SODs, and each of these SODs is called atomic decomposition. With the following property. Namely, for any morphism F from Y to X in V, there is an atomic decomposition dpx given by A1 up to AN. And an atomic decomposition for Y. So dby given by K1 up to Km, and then pullback of A1 up to pullback of AN, where so K1 up to Km are like SOD of the kernel of the push forward. Okay, so this is the definition of atomic theory. So so you see, like, so what we what is asked that whenever you have or like that there exists an atomic decomposition for X, and there exists an atomic decomposition for Y, such that, like, when you write it as kernel of push forward and pullback of the base, that then you get exactly the pullback of the base, like piece by piece, and you split the kernel into a certain number of pieces. Okay, so I know, like, so if there are questions, please ask. Okay.
I would like to ask something.
Yes.
You say there is an atomic decomposition, but isn't it why there is? I mean, isn't it the atomic decomposition because for each object there's only one mutation equivalence class?
Yeah. Okay. So what I mean here with atomic decomposition, so like each element, so each SOD is called an atomic decomposition.
In the same equivalence class.
Yes.
So you choose a representative in the mutation equivalence class.
Yes. So I say like there is a representative such that it is
In that class. Yeah. Okay. Understand. Thank you.
More questions? Okay. So now the theorem. And okay, let me call it theorem B. Is now that it exists, and a bit more than that. So the theorem is like this. So there is atomic theory for, so I have to say for which category V I look at. So let me call it for V smaller equal to 2, K. So where the objects are given, so the objects are varieties over K. They are of dimension at most 2. And the morphisms that we take, so we don't take all derived contractions, but we take what we call a rational derived contractions. And so these are just exactly compositions of MMP steps. Okay, so what I say is that when we take varieties, so surfaces and of smaller dimension, and as morphisms, we just take all compositions of MMP steps, then we can construct an atomic theory. And I should say K is a perfect field. Okay, perfect. And so a bit more holds, moreover, the constructed theories are compatible with algebraic field extensions. So, okay. Okay, so what I mean here is like, now for any perfect field, we construct an atomic theory, so we construct all together. And when you have the theory for K and you have the theory for L, then these are compatible in a sense. Okay, so are there questions to the theorem?
Why do you call the morphism rational? I mean, the right contraction, I understand, but I mean, these are morphisms, not rational maps, correct?
Yeah, because so how is it? Because so it's a derived contraction such that the generic fiber is geometrically rational.
I see. Thank you. And when you say varieties, you mean smooth varieties here, yes?
Yeah, smooth projective, yes. Thanks. Okay, so I called this theorem B because in fact this is not the setting where we work in. So we work in the setting, in the G equivariant setting. So everything, okay, so we work in the setting of G surfaces. And we have two main kind of group actions in mind. So the first one is we take G to be the absolute Galois group, or K a perfect field. And then we take the usual action on the, when you take the base change to the algebraic closure. And the other action we have in mind is we take subgroups of the automorphism group of X. Finite. And fixing K, and so this is over an algebraically closed field. Okay, so so this means that's also in the, so also when we okay, so here, so what do I want to say? So in these both cases, we work over an algebraically closed field, but we have a group action on it. Okay, and so then this theorem B that I gave. So first we do something for G surfaces, and then we make a descent to get it. So let me set up now the G equivariant things. So now basically it's just like everywhere we add some G. So we add here G varieties. And now so all morphisms are G equivariant. Then we call it a G atomic theory. Or we take G invariant SODs. Okay, and so in this way we define a G atomic theory. And the theorem that we get in this, like in that setting, so I call it theorem A. So there is an explicit G atomic theory for now the category, let me call it V smaller or equal to 2G. So now the objects are G varieties of dimension at most 2, and the morphisms are G equivariant, a rational derived contraction. And so now this means composition of G MMP steps. Now, so for completeness, I can also say what G MMP steps are. Which color? Blue. Okay, so GMMP for surfaces. So we have G equivalent. So this is G equivariant. Now instead of closed points, we have G orbits of points. And the Mori fiber space has to be G equivariant. So I mean this morphism has to be G equivariant, and we take the G pica rank to be 1. And I think maybe this, I didn't forget to add a G. Maybe I did, I don't know. Okay, so so we work in this, we work in a setting of G surfaces. So let me give some applications that we have to birationality questions. Or I first want to do another example. Let me do an example. Let's say again we have P2. And now let's take a point. Let's take it. Okay, let's take G to be maybe Z mod 2. And let's say we have a point. We have a G orbit of size 2 that we want to blow up. Okay, so let's blow it up. So this is now a Del Pezzo surface of degree 7. And so here we have like the line that goes through this G orbit. And so this line is a G invariant, which means that, okay, so if we blow up the 2 points, we have like 2 -1 curves like this, and the strict transform of the line through 2 points. This is also a -1 curve. So we can contract this line equivariantly. And we go to a quadric, so we go to P1 times P1. But now what happens is that the 2 rulings of P1 times P1 are now exchanged by G. So in this way you get an example with so G P1 times P1 is 1. Okay. So this is an example of a so this is an example of a G Mori fiber space. So with this action of G to spec K is a G Mori fiber space. So what can we say about the derived category? So again, for the derived category of X7, we have now 2 ways to write it. So on one side, we can we use the blow-up formula and we get the pullback from P2. So we have, so let's give a name to this map. So let's call it F and G. So we have, okay, and let's maybe say these are E1 and E2. And on the other side, we contract the line, this line, let me call it E. Okay, so again, so when we look at the pullback from P2, we get OE1 -1 and OE2 -1, and then the pullback from P2, so O -2H, O -H, and O. And so now what happens with this? So I write the kernel of the push forward. I write them as a block because they are orthogonal to each other. So they're the order of the two. It doesn't matter. In the SOD, you can exchange the order. And now also what happens is that G it exchanges the two. So this is a G invariant block. And yeah, and so when we look at P1 times P1 with this group action, so we have P1 times P1. So we can write this. Let me write H1 and H2 for the two rulings. And so again, because G exchanges the two rulings, this category here is you cannot decompose G invariantly. And so and then pulling it back, it gives you again another SOD on X7. Okay. So now I want to say some things about applications to birationality. Or to rationality, so birationality. So one proposition that we get is the following. So if X is rational, so now this is for a K-perfect field. So it is rational if and only if all atoms of X are of the form dB of L for some finite field extension. Finite field extension. So in the example I just gave you, so atoms, I didn't say what atoms are. So atoms are just the pieces of an atomic decomposition. Okay, and so in the example before that I gave, now let's say, I mean, okay, we can, for example, okay, so now here I said that G is Z mod 2, and so we can also think of this, for example, the absolute Galois group of the real numbers, right? So we can have like a complex conjugate point. And so what we do is we blow up a closed point of degree 2, and then we get this X7. And then we can contract the line and we get this quadric. And the atoms of that quadric are then so dB of K, dB of okay, so I should say, so let's take example. take G to be the Galois group of C over R. And okay, so K doesn't exist. So we have dB of R, dB of C, and dB of R. Because I didn't say, but all the examples I gave, so all of these decompositions are atomic decompositions. I guess I should have said this. Okay, so these are the atoms. And so the reason here is because when you blow up and when you contract, you only add atoms of this shape. So you only add atoms which are dB of L for some field extension L. So they correspond to the residue field of the point that you blow up. Okay, then maybe another proposition. Okay, or maybe I rather go to the proof of how we construct our atomic decompositions. So proof of theorem. So the step 0 is that we need to show it for curves. Or we need to say what are the atomic decompositions for curves. And so here we don't have any choice. So if we have a curve C of genus at least 1, then dB of C is not decomposable. So the atomic decomposition is just dB of C. So this is atomic. And if C is P1, then we also don't have a choice. So then we take dB of P1 to be O minus 1 and O. And we don't have a choice because P1 to spec K is a Mori hyperspace. Okay. So if you want it to be compatible with Mori fiber spaces, then we need to split dB of P1 into two parts. Okay, so this is step 0. Then step 1. So now we make the definition on the outputs of the MMP. So for minimal models and for Mori fiber spaces. So for minimal model, so when Kx is net, we do not decompose. So we take dBx to be atomic. So even sometimes you could decompose it, but we do not decompose. Okay, and for Mori fiber space, so if X2B is a Mori fiber space, so maybe I should say, so I speak now of theorem A, so I have a G Mori fiber space. So I remind you that we have that dB of X, it is given by the kernel of the push forward and the pullback of the base. And now, since in smaller dimension, we already have atomic decomposition of, we already have an atomic decomposition of the base. So this is we need to take what we did in step 0. And then the question is like, what do we do with the kernel? Like, do we split it more? And so what we do is the following. So we have some cases. So G-Mori fiber spaces, they are either, okay, so if B is a point, then this means exactly that X is a del Pezzo surface. Say of degree D. And with rho G is 1. Okay, so this is one possibility. And the other possibility is that we have a conic, so B is a curve, and then we have a conic bundle. So of G pica rank 2. So these are two cases. Now, when we are in the first case of del Pezzo surfaces, I distinguish again two cases, namely either sorry. So either the degree, I'm sorry. So either the degree is small or it is large. So D at most 4 or at least 5. And so when the degree is small, the atomic decomposition that we take, it is just so we need to take the structure sheaf because this comes, because again, X to spec K is a Mori fiber space, so we need to have what comes from spec K. And then we just take the orthogonal complement of it. And for E at least 5, it is a bit more we have different cases to consider, and what we do is we take the 3-block decomposition by Karpov-Nogin. Okay, and for the conic bundles, we have also, so either the base is a P1, and then again we get del Pezzo surfaces. We distinguish again the cases small and large degree. And then we get either, so here we get 3 pieces. Four pieces, and when we have genus at least 1, we just get 2 pieces. So then this means that we don't split the kernel in that case. Okay, so this is so this is what we do is first we define it on the outputs of the MMP. We say what are the what do we take as atomic decompositions. And then the second step, and this is the key part, is that we check Sarkis of links. So Sarkis of links, they are basically certain birational maps that we can decompose, or like that we can write as squares. So maybe we have Z over some base B. Such that the dimension of B is smaller than the dimension of Z. And each of these arrows is a GMMP step. Okay, and so what we need to check is that when we made the definition, okay, and so when we made the definition, okay, so like another way to write them is also in this way. So now that we have a Mori fiber space here, and then here we have a birational map. And so so we have that rho of Z over B, so this is 2. But in this way we have like two contractions over B. And what we need to do is, if we take the atomic decomposition of X1 and we take the atomic decomposition of X2, we pull both of them back to SODs of Z. And then we need to check that the two that we get, that these are mutation equivalent. And so for one example, so I showed you here somewhere. So in fact, what this example here, this is a Sarkis of link, because so here this is also a Mori fiber space. So here I have a 2 Mori fiber space in here, and so 2 MMP steps here and MMP step here. And so exactly what I told you, that here these two these two SODs that we get are mutation equivalent. This is exactly one of the things that we need to check. And also the other example that I gave you. So here, if I add the base, so the base here is spec K. Then again, we have 2 MMP steps on each side. And so yeah, what one has to check is that when you pull back the 2 atomic decomposition of P2 and this G P1 times P1, you pull them back, that they are mutation equivalent. So these are the type of things that one has to check. And now the nice thing is that Sarkis of links, there are like per surfaces, there is a finite disk going back to Wiskovsky. And so we just have to go through this list and do the checking. Okay, so this is the main part. This is, I think it's something like 15 pages of computations. And then step 3 is that we need to extend this atomic decomposition that we defined on the outputs to all surfaces. So when we have Y to X, and X is either a minimal model, or Y to X and X is a Mori fiber space. So then we extend it in the, well, I mean, now this map is composition of blow-ups of points. And so how we define the atomic decomposition for Y is So let's say you blow up here, I don't know, P1 up to Pn. So you have like, you take the decomposition that comes from X, and then you have O E1 minus 1, and so on up to O En minus 1. So in this is how we then define atomic decompositions on Y. Okay, then step 4 is we need to check that this is well defined. So when we have some Y with a birational morphism to some Mori fiber space X over B and to some X prime over B prime, we need to check that whatever we pull back here and here, that they are equivalent on top, mutation equivalent on top. And so here we use the Sarkisov program, which says that this birational map here, which can be very complicated, but we can decompose it into Sarkisov links. And in fact, the Sarkisov program for surfaces is such that this the surfaces you have on top, they are all dominated by Y. Okay, so in this way we can get this atomic decomposition on Y are independent on the choice of Mori fiber space that we end up with. And then finally, step 5 is to, well, okay, check the axioms. So I mean, like, check that the definition is satisfied. And check compatibility with subgroups. Yeah, so now this just, like, did I say theorem A? Yeah, so sorry. So in theorem A, I missed a part. So we do have an explicit G-atomic theory for varieties of dimension up to 2 with these GMMP steps, and moreover, the constructed theories are subgroup compatible. Or let's say are compatible with passing to subgroups. H inside of G. So this means, so we construct atomic theories for all groups at the same time. And then if you look at the one constructed for H and the one constructed for G's, they are compatible with each other in the sense that the one for the subgroup, it splits the one of the bigger group. Like, it's finer. Okay, so I think this is all I wanted to say. Thank you.
Thank you, Helia. Let's all give the speaker a round of applause now. If you have any questions, please ask them.
Can I ask something?
Yes.
Yeah. So if you think of atoms as defined by Gromov-Witten invariance by looking at maybe the matrix defining K star, and then looking at the dimension of the eigenspaces, then I think conjecturally this is related to this definition of atoms. But does your thing give that the eigenspace decomposition also behaves well in this surface G surface setting?
So I don't know anything about this other side. So it's true that conjecture should be the same. But I mean, there are some. So no, I don't know. I don't know. Also, I'm not sure I understand. So which matrix do you take? Like
you take the matrix that defines. So if you have the quantum multiplication star in the quantum cohomology ring, and then you take the multiplication by the canonical divisor, then this can be written as a linear matrix as a matrix in the in some base, and then you can look at that matrix and ask what the eigenvalues are, and what the the multiplicities of the eigenvalues.
yeah, so I think what it should correspond to is something like the number of I think the number of our atoms, they should correspond to the number of distinct eigenvalues.
Exactly. Yes.
Right.
Yeah, but my question is, I mean, somehow there are many semi-orthogonal decompositions, but not many atomic decompositions in terms of eigenspaces, and so these eigenspaces select semi-orthogonal decomposition, and I'm curious if it is this one you're also selecting. I mean, it's not so clear to me because I'm still learning how this works, but my impression was that if you start from the eigen decomposition, there's some kind of path you can follow to conjecturally get these the semi-orthogonal decomposition, and it would be interesting to see if it is this one that you get. Because
so I agree. So this would be, so like this is conjecturally, and but I don't know. So I don't know how to. I never did this computation. I don't know.
Okay, and so you also don't know if it is known.
So I think it's not known at least.
Okay.
So yeah.
Okay, thank you. Sorry for a complicated question.
No.
Thank you. Last question. Any more questions? Anybody? In that step two, with the surface of length, which you said takes up 15 pages, I mean, are there any hopes of simplification there, or do you think that is exactly how the group should be?
So you ask about the mutations that we do
Yes,
for the
yes.
series of links.
Yes.
So the thing is, so now I forgot. So I mean there are a lot of different cases. So there are a lot of different series of link that one has to do, and you have to do each of them individually. I mean, there are some that you can do together, but most of them are really like sporadic.
I see. And is this the thing that's in the appendix of your paper?
Yes, exactly. Yeah.
Okay. Thank you. Any other questions? Anybody? If we don't have further questions, let's thank our speaker once again. So we don't have a talk next week. The week after next week, we have Jenny Liu from Warwick. Bye-bye.